Okay, next speaker is Professor Vinayachandran. He's going to talk about submesoscale processes associated with the East Indian coastal current in the Bay of Bengal. Take it away.
Thank you. First of all, thanks to the organizers, Jim and the team, for inviting me to give this short lecture. Recently we had an opportunity to carry out a high resolution model run thanks to the National Supercomputing Mission that's being organized by the Department of Science and Technology of the Government of India. So we have carried out a nearly 1 kilometer resolution model run of the Bay of Bengal using a regional ocean modeling system. And that's what I'm going to present here today. So this work is, this was started by postdoc Subrat Malik, who is at FSU currently. He's started the model setup, and which was taken over by Srikanth later on, and Bijit Khalida is a PhD student who is also working on this project now. So the forcing of the Indian Ocean is time dependent. The winds are monsoonal, and they blow towards India during the summer monsoon months of June to September, and they blow from the land towards ocean during the northeast monsoon months during November to February. So in response to that wind, the ocean circulation is continuously changing. So we have the monsoon current which flows, summer monsoon current which flows generally eastward during summer, and it reverses to be westward during winter. Now, these seasonally reversing monsoon winds and the associated weather pattern have a very distinct impact on the regional hydrography. So the rainfall is mostly concentrated on the eastern part of the Indian Ocean. So you can see the very high rainfall sitting near the mountains of, one is in the eastern Bay of Bengal and the other in the eastern Arabian Sea. So the sea surface temperature pattern is such that there are these strong upwelling systems sitting along the western boundary due to the strong Somali current here and upwelling of the coast of Arabia. So owing to that, the western side of the Indian Ocean is cooler compared to that on the eastern side. So the eastern part of the basin is warm and it receives a lot of rainfall. So therefore, the eastern side of the Indian Ocean, that's the Bay of Bengal, has very low salinity compared to its western side. So the Bay of Bengal receives a large amount of fresh water, either from river runoff and in addition also from the rainfall. And this is a simulation using the model ocean model shows the climatological pattern of how that fresh water that flows along the coast of India during the summer monsoon months and also during northeast monsoon flows around the coast of India and then flows into the Arabian Sea. So one feature I would like you to notice from this figure is that the rainfall is during the month of June to September. There is a bit of a delay for the runoff to arrive, and the runoff peaks during the month of August. And during August, you would see a lot of fresh water reaching this point, and then they flow down. However, during the summer monsoon month, they don't flow down all along the coast. They are kind of arrested somewhere halfway along the coast, and they only flow down completely along the coast of India after the summer monsoon months withdraw and the winds become northeast monsoon. So this is the beginning of the summer monsoon. There is quite a bit of fresh water coming and they flow down. And the fresh water then peaks during August. Then you would see the freshwater plumes here. And then after the summer monsoon withdraws, this would flow along this coast, all along the coast. Now, the freshwater that the bay gets has major implications on the upper layer, mixed layer structure and the air-sea interaction. And there is showing a sample profile before and after. These are observations made during 1999. Before the arrival of the fresh plume, there was an isothermal layer and isohaline layer, which was roughly 30 meters deep. And once the river plume arrives, the mixed layer becomes very shallow, basically owing to the salinity dropping by about 4 PSU compared to the state before. And then there is a very strongly stratified barrier layer sitting just beneath the mixed layer. So this is a basic character of the Bay of Bengal during the summer monsoon. The mixed layer becomes very, very thin. It doesn't cool, and it can warm rapidly during the intermittent sunny periods during the monsoon, supporting weather systems one after the other. So I think we have, this hall might have heard quite a bit on submesoscale. So this is a brief summary from the paper by Jim McWilliams, which portrays where the submesoscale lies in the spatial and time domains. So this is the mesoscale here, and then the submesoscale. So this is mostly non-rotational and unbalanced compared to the large scale circulation, which is rotational and balanced. So this is between the mesoscale and the microscale where the dissipation is starting. So ocean processes and features with the horizontal and spatial scales of roughly 0.1 to 10 kilometers and the temporal scales of hours to few days are generally termed as the submesoscale. Now they manifest mostly as fronts, filaments, and eddies, and they are characterized by Rossby number of the order of 1 and large values of relative vorticity and vertical velocity. So these are important because they could be responsible for significant redistribution of active and passive tracers, and also for the restratification of the mixed layer, thus affecting the sea surface temperature and air-sea interactions. So in addition, they could also be responsible for significant redistribution of, it's the same thing, sorry. So for providing the pathway for the forward cascade of energy from mesoscale to dissipations. So submesoscales are basically generated by frontogenesis, which is due to the sharpening of density gradients by the convergent confluent flow, often by mesoscale eddies, then mixed layer instabilities such as overturning and symmetric instability. So for this presentation, since we have used a model simulation, basically I'm going to show the characteristics of the submesoscale and looking at some of these processes which can lead to the generation of submesoscale in the Bay of Bengal. There have been some reports which indicated fairly strong submesoscale activity in the Bay of Bengal. There have been some observations, Ramachandran et al. And Sengupta et al., who suggested that there are fairly strong submesoscale generating fronts in the Bay of Bengal. So Sarkar studied submesoscale using a model simulation and looked at the horizontal and vertical structure of the structures using salinity fronts. Jensen used a couple model to look at the effect of atmospheric and oceanic phenomena that's associated with it. And there's another interesting paper by Pham who looked at this generation of secondary circulation associated with the submesoscale. So this is a picture from the paper by Lee et al., which basically shows the MODIS images on several instances. One is on November 11, 2020, other one on January 30, 2018, which shows several of the submesoscale structures with the small spatial structures. Now, briefly about the East India coastal current. The East India coastal current flows to poleward during the spring months of February to May. And that's the time the current is best organized. It flows as a western boundary current right from the northern tip of Sri Lanka all the way to the Bay of Bengal as a fairly well organized western boundary current of roughly 200 kilometers wide and speeds between 50 centimeters to 1 meter per second. Once the monsoon sets in, the current breaks down. So the flow still remains to be northward in this part of the course, associated with a reasonable amount of upwelling. But further north, it is the river plume that is flowing down. Once the southwest monsoon withdraws, the current flows all along the coast of India as the low salinity water carrying East India coastal current. Now, one interesting feature that came out of the analysis of the along track satellite data by Fabian Durand is that the current is not like that you see a nice one characterized by the smooth lines, but is made up of several eddies. And these eddies are rotating in either anticyclonic or cyclonic direction, and it is these mesoscale eddies moving one after the other that is constituting the East India coastal current. So this has been looked at by altimeter data, which has its own benefits and disadvantages, but there haven't been much data to document this completely. Now, for this talk, we are going to use a simulation from a regional ocean modeling system, and this is the complete Bay of Bengal. 77 to 99 east, 4 north to 23 north there. So the model has a resolution of approximately 1 kilometer, 1 by 96, with 40 vertical levels. So these computations take a long time, and here we have simulation for just 2 years, starting from January 2012 and running up to 31st December 2013. These two boundaries, one on the south and the other one on the west, are open. Initial and boundary conditions are taken from the HICOM simulations. And for surface forcing, we use SCAT winds and the rest of the variables from the ERA interim. Okay. Now, here's a comparison of how well the model is doing in terms of simulating the basic variables. So this slide is for the SST. So these top ones are data from the GHR SST data, again 1 kilometer resolution. And these are daily model outputs, and the middle panels are from the model. So one can see that there is good correspondence between the patterns of models and observations, as you can see them. And here is some statistics which shows the standard deviation from the data, from the model, and the RMS deviation from the model. So the RMS deviation is given on the slide here, which goes to a maximum value of about 2 degrees. The salinity simulation needs improvement because there are issues with them. One of them is related to the river runoff. So the data there, what we have used is climatological, owing to the data of much better product. And also there are issues with how the model is handling, because we don't have explicit estuaries and so on. So we see good correspondence between the patterns during spring, but during the summer monsoon season. So again, the comparison is with Aquarius. So the model is a bit too fresh, but it does simulate the river plume as we see in the model. So the model needs a bit more improvement in terms of the salinity. So here is a validation for the currents based on the Oscar data. Oscar data is much coarser, about 1/3 of a degree. And so these patterns of the spring current, which flows, shows the western boundary current of during spring, and then the two directional patterns during the summer, and the flow of the East India current during winter. A bit more stringent comparison is possible with the buoy data. So this is there are 3 Rama buoys in the Bay of Bengal, 12, 15, and 18 degrees north. And here is a comparison for the year 2013. So there are some data gaps, but we are able to do some comparison. These left panels are for the sea surface temperature for the 15, 12, and 8 degree north buoys. So red one is from the model and the black is from the data. So there is a very good correspondence between the model sea surface temperature and the buoy data. But when we come to the salinity, you see that there is quite a bit of differences. So there is quite a bit of departure that you see from the salinity. So this is also owing to the circulation pattern, because there are times when either a front or an eddy which crosses the buoy, which could be carrying low salinity water, which is very hard for the model to capture. So this is the RMS deviation for the SST. That's about maximum is about 0.4, but when it goes to the salinity, these values are higher. So this is a similar comparison for the time depth section of the data and the model, and you could see the similar patterns. The model performance being very good, but there are differences in both the magnitudes and the times when the pulses of low salinity waters appears at these two locations. Okay, let's take this. Now, coming to the submesoscale, so this is the Rossby number, which is the basic parameter to characterize the submesoscale, given by the ratio of the vorticity, the relative to planetary vorticity. So this shows the Rossby number pattern for representing three times of the year: the spring, summer monsoon, and the northeast monsoon season. So during spring, we see some amount of submesoscale activity, and similar patterns can also be seen during the summer, but during November, it is very well organized all along the coast of India. Now, to separate the region that is influenced by the East India coastal current, what's been done is the region between the coast and the isobath of 2000 meters is chosen as the region affected by the East India coastal current. So there are three curves here, and one of them is for the entire domain that you see here as the blue one, and then this black curve is for the EICC region, and the other one is for the water column deeper than 2000 meters. So clearly, the Rossby number is much larger for the EICC region compared to the rest of the regions. In addition, we see that the strongest, the highest values are during the northeast monsoon season, starting from November and going up to about January. So similar seasonal patterns can also be inferred from this RMS and various and skewness. So the various clearly shows that the EICC region has much larger, stronger submesoscale activity compared to the rest of the way. The skewness shows the preference for a positive vorticity, which is typical of the submesoscale processes. There are other parameters which we can use to confirm this. One of them is strain rate, and then the divergence, and finally the vertical velocity. So all these parameters confirm that there is a certain amount of submesoscale activity during spring and summer, but they are strongest during the northeast monsoon time, and they are strongest along the coast of India, where the EICC is flowing down. So all these figures support that inference. Now, other parameter, which is the frontal sharpness, which is very much relevant to the submesoscale processes, where the sharp gradients during summer. So this is during summer when the freshwater plume flows down, which is associated with a fairly strong magnitude of the frontal sharpness. And then very clear pattern of frontal sharpness all along the coast of India during November, but they are much weaker during winter. So this frontal sharpness starts increasing during the summer monsoon month, with a lot of fluctuations owing to the arrival of the freshwater plume, and they decrease slightly during the northeast monsoon time. So the sharp gradients that we see during the summer is owing to the river plume that flow down along the coast of India during that time. So we have looked at these mechanisms which can lead to the submesoscale processes, and first among them is frontogenesis. As the front becomes unstable, taken the quote from the paper by Thomas et al. As the front becomes unstable and meanders, the nonlinear interaction of the lateral velocity shear and the buoyancy gradient locally intensified across front buoyancy gradient. So the parameterized that is useful to characterize this frontogenesis, the frontal frontal tendency given by this equations. So this is an indication of the tendency of the flow to strengthen or dilute the lateral density. So a positive frontal tendency is an indication of frontogenesis, and the negative frontal tendency is the opposite, that's a frontolysis. So there is very little frontogenesis happening during spring, and a strong frontogenesis happening during the summer monsoon in the northern part of the coast, and all along the coast of India happening during the northeast monsoon months. So this is the corresponding annual cycle for the EACC region, which again shows a certain increase during the summer monsoon months, and the mean above the other two curves during the northern monsoon time. So on the whole, the average tendency remains positive over the domain, and the EACC has high values. The other process that can lead to generation of submesoscale is the mixed layer instabilities owing to the strengthening of lateral density gradients. So these mixed layer instabilities can tend to slump the horizontal gradients into vertical and thus restratify the mixed layer. So whenever that happens, it can lead to secondary agiostrophic circulations around the fronts and sharp gradients. So the way to quantify mixed layer instability is to look at the amount of available potential energy that can be converted to kinetic energy associated with the secondary circulation. And this is denoted by the quantity pk given here, which is given as this integral. So here W prime and B prime are these quantities indicate submesoscale component, and the averaging is done over space. So in order to separate the flow or extract the submesoscale part of the flow, so we have used a two-dimensional low-pass Gaussian filter with a scale of 8 km. And this 8 km is a Rossby radius of deformation obtained from NH by F, where N is the Brunt-Bois-Sala frequency average over the mixed layer, and H is the mixed layer depth. And that quantity is shown by this red curve here shown in this graph. So Fox-Kemper proposed that one can use a scaling associated with the submesoscale secondary circulation, which is basically related to the horizontal gradient of the buoyancy and also the mixed layer. So the thickness of the mixed layer and the strength of the buoyancy gradient can be used as this, and that is given as this blue curve, which is shown here. So whenever the submesoscale activity is very strong, the scaling proposed by Fox-Kemper matches well with the energy conversion. And the generation of the mixed layer instabilities is very low during the spring months, and they picks up slightly again during the summer monsoon time, and picks again during the winter monsoon. Mesoscale flow features such as eddies can also generate submesoscale owing to the increased straining of the flow and slumping of horizontal gradients, and this was proposed by McWilliams. And McWilliams also proposed two scaling, one of them due to the mixed layer instabilities and the other one owing to the mesoscale straining, and also proposed the vertical flux of buoyancy owing to these two quantities. So, so we see that fairly strong values of the mixed layer instabilities during summer, and corresponding strain also during the summer monsoon time. But when we look at the vertical buoyancy fluxes owing to these processes, we see that there is a certain amount of implication to submesoscale during the springtime, owing to both of these processes, instabilities and strain, and they are very weak during the summer monsoon time, but again strong all along the coast of India during the northeast monsoon season. So to pursue this further, now there is a bit of a problem that in spite of the strong river plume sitting in the northern part of the coast during summer monsoon time, they are not very clearly indicate of strong vertical buoyancy flux. So this is a picture of the symmetric instability. Symmetric instability is possible whenever the potential vorticity is negative. So when we look at this graph, we see that the potential vorticity is either 0 or positive during spring, and they are mostly positive during the summer, most part of the coast, except for a small patch that you can see along the coast. But during November, it is negative everywhere. So this suggests that the potential vorticity provides a condition, negative potential vorticity provides a condition favorable for the submesoscale owing during the northeast monsoon time. Thomas proposed that it is possible to identify the certainty of the submesoscale generation by looking at the critical Richardson number. The potential vorticity provides only a necessary condition for the generation of submesoscale. So according to that condition proposed by Thomas et al., so the critical Richardson number can be used to obtain, to identify whether the conditions are favorable for submesoscale or not. So when the stratification is stable and the vorticity is cyclonic, submesoscale instability develops when the condition that the critical Richardson number is between the Richardson number is between the critical value and -90. And if the vorticity is anticyclonic and Ri is between -45 and phi c, and then it is favorable for the generation of hybrid, symmetrical, inertial, or centrifugal instability. And for unstable stratification, and these are the conditions. So to check that for the Bay of Bengal, so so this is the picture which shows the regions where the criterion for symmetric instability is satisfied. So during summer, along the several patches during spring, along several patches along the coast of India, there are conditions are favorable for the generation. But during summer, it is much weaker. Again, well organized all along the coast of India during the winter monsoon time. Now, this third row shows the proportion of days in the season when the conditions are favorable for submesoscale instability. So this is within a season, for in the 3 months period, how many days it is possible for the submesoscale to be generated. So they are close to 0 during summer, very few during the spring, and very high during the northeast monsoon time. So this is more or less like the third law, except that this is the condition for the initial and hybrid instability. So the summary is that basically we have done a 1 kilometer resolution for the Bay of Bengal, and that simulation very clearly shows that East India coastal current is a region which has a very high potential for a strong generation of submesoscale activity. And that submesoscale activity has a very clear seasonal cycle which peaks during the winter monsoon time. So, then we have looked at photogenesis, MLI, and SI, and these two seem to have major contribution for the generation of submesoscale activity. So the most surprising result is that the river plume is most active during the summer monsoon, when it is a fairly large plume sitting off the northern part of the coast, and that's when it is causing the very thin mixed layers and everything. But that is not the time when the submesoscale activity is very strong. So one question that is facing us is that what would be the implication of these submesoscale activities in terms of converting into sea surface temperature patterns, what would be its influence and so on. So I would stop there with one last slide showing the expanded view of an eddy during the month of November. So this eddy started from the south, and then it moved along, and it had these bands of very strong horizontal density gradients. Thank you.
All right, we have time for one or two questions.
Okay, in the beginning you showed validation of SST, which worked fine, and as validation with salinity, surface salinity, right? Compared to the satellite data, there was a bias, but how trustworthy is the satellite data close to the coast at this river plume?
Yeah, it's a very good question. The satellite data is from Aquarius. It has much coarser resolution. It has its own problems, particularly near the river mouth. But we believe the salinity simulation need to be improved based on our various comparisons and so on. So the data from Rama is very good data. So the Rama buoy data is high quality data, even though they are point-wise data. So even there, the simulations are showing that more or less consistently large differences between the simulations and yes. So I agree that the comparison with the satellite data could be biased by the errors in satellite data, but the model needs improvement in terms of the salinity simulations. So there are multiple factors there. One of them is the accuracy and the methodology of how the river plume enters the bay, and also the patterns of circulation. The circulation is made up of many eddies in the Bay of Bengal at all time scales. Mesoscale eddies are almost everywhere there. So the timing and whether these eddies trap the low salinity pools or not is also a factor which is affecting those comparisons. Yes.
Other questions? All right. If not, let's thank again the speaker.